Hi guys. So this is the net force lesson from week 11. Excuse me. You guys had the homework to do the Frayer models on IMB 18, 19, well, the Frayer models were on IMB 19 and 20. On IMB 18 was our reading. So you were doing a close reading of forces in motion. We're looking at this question: why do objects speed up, slow down, or change directions? Force is a term you are probably familiar with. So I'm not going to spend a ton of time talking about it, but I will point out that the textbook defines force as a push or pull between objects. And then the other thing I'd like to point out is that applying force on an object does not always result in motion. You have to account for all of the forces acting on an object before you can predict its motion. And so one way that we can show this is using force diagrams. So force diagrams help us find the net force. And so the net force is the sum of all the forces acting on an object. And so when you're looking at a force diagram, the arrow's length determines its strength. So you can see here that this arrow is longer than this arrow. So it's a stronger force. And then the direction of the arrow indicates its direction. And so these two forces are acting on each other, against each other. They're pushing against. And so we use newtons as our unit of measurement for force. You can also use pounds, but we'll be using newtons. And so this force is 8 newtons, and this force is 8 newtons. And because they're pushing against each other, they are canceling each other out, which results in a net force of 0 newtons. And anytime you have no net force, you have no motion. This brown text here, this brown box or book here, you have clearly a stronger force on one side than the other. And so we can tell right away that this book is going to move to the left because this force is stronger than this force. And we can determine by how much it's going to move by looking at our force measurements. So our short little arrow here, this is 2 newtons of force, and this is 8 newtons of force. Because they're moving in opposite directions, they're pushing against each other, we're gonna subtract this 2 from this 8 because 2 of these newtons are canceling out 2 of these newtons. So we end up with a net force of 6 newtons. And then again, the book is moving to the left. So that's what the bulk of our work today is going to be looking at force diagrams, calculating net force, and predicting motion using force diagrams. For our vocab terms, force, again, this is a term that you are more familiar with, so we won't spend too much time on there. Remember, it's a push or pull between objects, which is why I have a car being pushed and a person pulling on a rope. When it comes to non-examples typically are the opposite of, or the antonym of that term. And so if a force is a push or pull between objects, then the opposite of that is going to be where there is no push or pull happening. And where we can see that is in space. So we have an object that floats in space with no forces acting on it. That would be the opposite of force. This one we're going to spend a little bit of time on because I really do want you to have an understanding of net force. Net force is a new term for us. We use net force to calculate motion. and predict motion. So net force is the sum of all the forces acting on an object. And we use force diagrams to show net force. Force diagrams are great because they help us visualize the problem. And so I've got this example here where we have a purple box being pushed and there's friction. The length of the arrow determines the strength of the force. You can see this arrow is longer than this arrow, so it's a stronger force. And then the direction of the arrow indicates the direction of the force. And so because these are moving in opposite directions, they're moving against each other. The first thing I do when I look at a force diagram is I determine what direction is this object going to move. Well, because this force is stronger than this force, I know the box is going to move to the right. So we have a rightward motion. I can calculate by how much when I look at the measurements of force. And so we have a pushing force of 5 newtons here, and then a friction force of 2 newtons here. And because they're pushing against each other, we're going to subtract those values. So to find our net force, we're going to take 5 newtons and subtract 2 newtons, and we'll end up with a net force, a total force of 3 newtons to the right. An example of net force I like to use is Coach Maurice and I, just because there's such a stark difference in our size and strength. For an example, him and I are pushing on an object in opposite directions. I'm on one side, he's on the other, and we're pushing. But because he's much stronger than I am, the object that we're pushing is going to move in the direction he's pushing. That is the result of a net force. So if net force is how we describe motion or calculate motion, then the opposite of that is going to be no motion. So when an object has no motion, that is the opposite of net force. Another way we can describe that is by saying balanced forces. So the bulk of our work today, we're going to be looking at force diagrams like this and calculating net force. So on IMB 21, you have this example. The caption says this diagram illustrates the effects of balanced and unbalanced forces on an object. Each green arrow points in the direction that one force is applied to a ball. A longer arrow indicates a stronger force. The net force shown in purple is the sum of the applied forces. So green arrows are the forces acting on the ball. The purple arrows are the net force. And then I've added this annotation here, balanced forces when the net force is 0, and unbalanced forces when the net force is greater than 0. So we're determining whether the forces on each ball are balanced or unbalanced. I'm actually gonna back out here. So when we look at this first example, we have 2 green arrows moving in opposite directions. They're both pushing on the basketball, but we can see that the arrows are equal in length, which means they're the same strength, resulting in no net force. So because the forces on each side of the ball are balanced, and we have no motion, we can say that these forces are balanced. When there's no motion, the forces are balanced. On this one, this next one, we have the forces pulling on the ball in opposite directions. They're pulling away from each other. But again, we can see that the arrows are equal in size, which means they're the same force. This results in no net force. When we have no net force, there's no motion. No motion means balanced forces are at play. So when we have we have a net force, that equals 0, we know that the forces are balanced. In C, it's a similar situation. We have forces moving away from each other, but we can see right away that this force is stronger than this force, which results in a small, but still there, net force. This ball is going to move to the right. When we look at this object, we can see that. So because the forces acting on this object are not equal, we're going to say that these are unbalanced forces because we have motion. Anytime you have motion, that means the forces acting on the object are unbalanced. Here we've got the forces pushing on the ball. One side's pushing really hard. This is like coach on one side and me on the other, right? Coach is pushing, pushing, pushing. I'm pushing, 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 but he's just so much stronger. So the ball is going to move to the left. Anytime we have some net force, that's going to result in unbalanced forces. So with the net force being greater than 0, we know that we have unbalanced forces. About the forces acting on the object are not the same. This example, kind of a trick example, the forces are both pushing in the same direction. We have not seen this yet. We've got forces pushing on the ball in the same direction. And this is resulting in a large net force. And so the ball is going to move to the right. This is like if we kicked the ball and pulled the ball at the same time, you would end up with the ball moving very quickly to the right. And so these are unbalanced forces because we have motion. Anytime we have motion, we know that the net force is greater than 0, and that is an unbalanced force. And so hopefully we're starting to have a deeper understanding of what it means to have net force. Net force is anytime there's motion. And then working with that, understanding and bringing in now these terms, balanced and unbalanced forces. All right, in IMB 22, we are calculating the direction the object will move and its net force. So we're looking at these examples here, A, B, and C. We have forces acting on all of these boxes. The very first question I ask myself is, what direction is this going to travel? Which force is stronger? Well, I can look and see just by the length of the arrow that the arrow pulling to the right is longer, which means it's a stronger force. So that means this box is going to move to the right. So I know the force pulling on the right is stronger, but by how much stronger is it? So I'm going to look at my measurements. I have 200 newtons here, and I have 30 newtons here, excuse me. They're pulling in opposite directions, which means 30 of these newtons cancel out 30 of these newtons. And so I can see that this force is 170 newtons stronger than the other one. And I'm subtracting, I'm doing 200 newtons minus 30 newtons because the forces are moving in opposite directions. Spelled that wrong. All right, I'm gonna move my little box. And then anytime I have motion, I know that they are unbalanced forces. And I can tell the forces acting on this object are not equal. And so those are unbalanced. On this next box, we can see that both forces are pulling in the same direction. This is similar to this one. This one we had a push in one direction and a pull in the same direction. And this one, they're both pulling in the same direction. So if I look at this, I can clearly see that this box is going to move to the right because all of the force is pulling it to that direction. So we have a rightward moving direction of travel. And then I'm looking at my net force and thinking, okay, it's moving to the right. Both of these forces are moving in the same direction. And because of that, what I'm going to do is I'm going to add my forces. So I would add 6 newtons plus 4 newtons to get 10 newtons. And I'm adding because the forces are moving in the same direction. Let's make this a little bigger. There we go. All right. And then again, because I have a net force, anytime you have a net force, anytime the net force is greater than 0, you have motion. Anytime you have motion, it indicates unbalanced forces. And so that's what's happening here. We have unbalanced forces, which is resulting in motion. If we look at box C, we'll give you a minute and see if you can solve this one on your own. All right, hopefully you said that the box is going to move to the right because this force is stronger than this force. 30 newtons stronger, and you can even just look at the length of the arrows there. And so we've got a box that's going to move to the right, but because we have this force counteracting some of this force, we've got to subtract because we're moving in opposite directions. So these are canceling out some of these newtons. And so we end up with 20 newtons of net force, 30 minus 10. And then again, we have motion, so we know these are unbalanced forces resulting in motion. So we look at slide 23. Hello. I apologize for the barking dogs. IMB 23, you are defining balanced and unbalanced. Remember, balanced forces are anytime there's a net force of 0. You have no net force, you end up with balanced forces. There's no motion. We have unbalanced forces. You have a net force greater than 0, resulting in motion. And so you can come up with some different examples for balanced and unbalanced to help deepen your understanding of those terms. Hopefully this helped you better understand what net force is. Again, net force is what happens when you add all the forces acting on an object. You can calculate its net force, and that will help you determine whether or not an object is moving or stationary.